So in section 5.3, we're going to talk about diagonalization. The math here looks kind of abstract, but this is some of the math that's behind all that Markov chain stuff that we've been talking about. It showed up with the chess question. It showed up with the zombie apocalypse in the high school. It showed up with the PageRank algorithm that your writing assignment is on today. So all that stuff is at some level tied to this concept of diagonalization. It took me a long time to realize that. So I'm excited that I now understand it well enough that I can tell you why this stuff actually matters. So let's start with a super simple example. Suppose we have the d given above and I want to find d squared. So d squared would be 3004 times 3004. What's the product? So I have like row times column is 9. And then row times second column, 3 times 0 plus 0 times 4, that'll be 0. And then come row times column, that's going to be 0. And then the last one is going to be 16, I think. Okay, yeah, from Gerline, thank you, 90016. And what I want to point out specifically is that this is the same thing as 3 squared, 0, 0, 4 squared. And so notice these 3's and 4's are the same as those 3's and 4's. So I'm hoping, using some complicated pattern matching, you could take a guess at D3. So this would be like 3 to the third, 0, 0, 4 to the third. Okay. In DK, similarly be 3 to the K, 0, 0, 4 to the K. Like, I know sometimes I say something's easy, and you're like, yeah, easy for you, Dust. But I think that powers of diagonal matrices are legitimately really easy. Like, you could explain how to do it to your, I don't know, 9-year-old nephew, and they might not know why, but they'd be like, oh, sweet, I'm doing college, right? So this stuff's pretty easy to do. And we're going to come back to this, but I want to remind you that when you're doing an iterative technique, think back to the chessboard, right? Like the knight is hopping around from place to place, 2 over, 1 up, 2 over, 1 up, 2 over, like when it's doing this little chess thing, each of those iterations is like doing a linear transformation, right? And each time you do a linear transformation, that's like multiplying by a matrix. And so you can think about this kth power here as that kth power is like doing the same process k times, like k iterations on the same thing, k moves of the knight, k minutes of the zombie outbreak, k different random clicks on the internet to see what happens. Okay. So if A equals P times D, P inverse for some invertible P and diagonal D, then A to the K is also easy to compute. First of all, in this case, we would say that the A and the D are which kind of matrices? Yeah, from Gerald. They're similar. So this is a connection between what we did just before this and now. So they're similar. So let's see, why is a to the k also easy to compute? So let's do a little bit of an aside. So if a is equal to p d p inverse, then a to the k would be the same thing as p d p inverse to the k. And let's just write that out a little bit. So this would be like p d p inverse times p d p inverse times dot 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 times p d p inverse k times. Okay. And what I'd like to point out is that we have these p times p inverses showing up. And every time you have a p times p or p inverse times p, what are you going to get out? From Tommy, I'm going to get out the identity matrix. Thank you, Felix. So not 1, but I, right? You're going to get out an I. And so I'm hoping you can see that this would be the same thing as p times d to the k times p inverse. Okay. What kind of matrix is D? D is that diagonal matrix. Powers of diagonal matrices are super easy. So instead of having to do powers on A, which is some complicated matrix that's going to take tons and tons of multiplications and additions, it's going to be super computationally intense, I can do all the power stuff just on the D, which is super easy, barely an inconvenience, and just be left having to do a couple of extra multiplications at the front end and the back end. Questions? Okay. So let's do some practice. So if we let a equal to 7, 4, -3, -1, I want to find a formula for a to the k given that a equals p d p inverse. And here I was really nice. I'm giving you the p and the d. And so Evan asked, how do I know that D was a diagonal matrix? It's because right there it says D is a diagonal matrix. So I'm just going to believe the directions. I haven't figured out how to find it yet. I'm just telling you so far. So, all right. Well, we actually just figured this out, right? We just learned that a to the k is equal to p d to the k p inverse, right? P d to the k p inverse. Okay. And so this is going to be equal to p -2, -2, 3, 1 times d to the k, which would be 1 to the k, which is just 1, 0, 0, 5 to the k, times p inverse. Let's see, determinant is -7 plus 12. What? One over 5? Oh, p inverse. Sorry, I'm finding a inverse. Not a inverse, but p inverse. -2 plus 6, 1 over 4, times 1, -2, 2, -3. Okay, thank you all for helping me with my arithmetic. So far, so good? You could multiply all this stuff out if you wanted. We're not going to mess around with that. That's not a good use of our time at this stage. So the real question here, in my mind, is where did this P and this D come from? So yay, good to hear that, Croy. So let's see if we can figure out where P and D come from. So I'm going to start by looking for the eigenvalues. Insert. And these are the eigenvalues of matrix A. So to find the eigenvalues of matrix A, I need to solve 0 equals the determinant of, what is it? 7 minus lambda, 4, -3, -1 minus lambda. Like that. Okay. So this is, looks like it's lambda squared minus 6 lambda plus 5. We multiply it all out, which factors to lambda minus 5, lambda minus 1. So I have 0 equals all of this garbage. So this tells me that lambda equals 1 and 5. Thumbs up. Look back for a second. 1 and 5. Oh, wait. Same 1 and 5. Right? The entries in the diagonal matrix, those are the eigenvalues. Okay. That's you're probably going to guess, gee, I wonder if P is going to come from the eigenvectors. Well, you're so smart. And you're right. But I think we're going to run out of time. So 2, we got to find the eigenvectors. So let's make sure that you remember what you're going to do. You're going to end up having to ref A minus 1 minus 1, come on, 1i, and you're going to ref A minus 5i. And what you're looking for is you're looking for the null space. Something like that. Okay. All right. So when we pick this up again on Tuesday, remember Monday is presentations. When we pick this up again on Tuesday, we'll continue to talk about diagonalization, but I think you already have a little bit of a sense for how all this stuff works together. We learned about eigenvectors and we learned about eigenvalues. because they help us do this diagonalization, which in turn helps us to run these iterative processes like the Markov chains that showed up in the chess, the zombie outbreak, and the PageRank algorithm. So we'll work through the details. There's a lot of cool stuff here. There's way more cool stuff than we'll actually get a chance to spend our time on. But I hope that that was kind of a cool and fun way to end the week. Have a wonderful first weekend in March. I hope it's the best weekend of March 2021 you've ever had. And I just really appreciate the time with you. Feel free to hang around if you have questions. Have a great weekend. I'll see you all next week. Take care, everyone. So when last we were together as a group, we began talking about section 5.3 on the diagonalization of a matrix. And as you may recall, a matrix is diagonalizable if it is similar to some diagonal matrix D. So diagonalizable. It's similar, and when we said similar, what we're talking about is it's the same transformation, but with respect to a different basis. That's what it means to be diagonalizable. That's what it means to be similar. And you might say, how do I know if it's going to be diagonalizable? How do I know if it's going to be, if it's the same transformation? Well, good news, we have this diagonalization theorem. And so the diagonalization theorem says what we've kind of already observed, and that is that a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. That is, if it has an eigenbasis. So one way, if you connect a few dots, one way you can see this really, that can be really helpful, is if you have n distinct eigenvalues, then you know there are going to be n linearly independent eigenvectors, and since there will be n linearly independent vectors, you know that it will be, you have an eigenbasis, and so it's diagonalizable. So if you have n distinct eigenvalues, it's a done deal. If you don't have n distinct eigenvalues, you still could have an eigenbasis. It's just you'll have to work a little harder to verify that fact. So in fact, A equals PDP inverse with D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in P. And so this theorem right here is valuable because it tells you not only that it's true, it tells you how to generate the P and the D matrices. So it says that the D matrix are the eigenvalues of A, and it says that the P matrix, where'd it go? P matrix are made up of the eigenvectors that correspond. And I think we'll see an example of this in just a moment. Questions so far? Okay. These eigenvectors, since they are linearly independent, form a basis for Rn. something like that. So let's do an example where you can see all this stuff happen. So not a hugely difficult matrix, just a nice practice one. So we want to diagonalize the matrix, if possible, A equal to what follows. That is, we need to find an invertible P and a diagonal matrix D such that A equals P, D, P inverse. And we're super, super kind to you. We're going to tell you that the eigenvalues are 1 and 5. Okay, just going to help you out right from the get-go. So if you want to diagonalize a matrix and you have the eigenvalues, what we need to find are what? Like, what do we need? Exactly. So we need the eigenvalues and we need the eigenvectors to make this work. So let's start by focusing in on lambda equals 1. And so if we want to focus in on lambda equals 1, we're going to find our a minus 1I, which would be 1, 2, minus 1, 1, 2, minus 1, minus 1, minus 2, 1, something like that. And so again, what are we changing? We're subtracting 1 from each of those diagonal entries. And then we can row reduce. And you'll notice in this case, the second row is the same as the first row. The third row is the negation. And so when you row reduce, it shouldn't surprise you that you get 1, 2, negative 1, 0, 0, 0, 0, 0, 0, like that. And from here, we should be able to find two linearly independent, there's two free variables, so we should be able to find two linearly independent eigenvalues. Let me state that more properly. There are two columns without a pivot, therefore there will be two linearly independent eigenvectors. So your first, or what are the two vectors? I've got negative 2, 1, 0 from Ahmed. And then I've got 1, 0, 1 from Andrew. And lots of other folks chiming in as well. Thanks, Gerline, Ben, Mahi. And if you're still not seeing how we get these, if you're not able to find these quickly, feel free to hang around after class, and I'd love to just practice with you. This isn't supposed to be a trick, but if you somehow, if it didn't click when we did, when we did it, happy to just do a couple of practice questions with you. So what are these? These are the eigenvectors that correspond to lambda equals 1. These are linearly independent eigenvecs to lambda equals 1. And notice, since they're linearly independent, we could say here, we would say that lambda equals 1 has geometric multiplicity 2. Questions about so far? Questions about this? Come on. Okay. So are we done? No, we got to mess around with that lambda equals 5 bit as well. So here we're going to have a minus 5i, which will be minus 3, 2, minus 1, 1, minus 2, minus 1, minus 1, minus 2, minus 3. At least if my notes are correct. And that row reduces to 1, 0, 1, 0, 1, 1, 0, 0, 0. So what's our eigenvector here? So from Gerlin, I've got a minus 1, minus 1, 1. And there's just one linearly independent eigenvector here because there's only one column that does not have a pivot in it. So and what's the geometric multiplicity of lambda equals 5? What's the geometric multiplicity of lambda equals 5? Yeah, from Gerlin, Ben, Felix, Megumi, Richard, Tommy, and Gerald, I've got a 1, and that's because there's only one linearly independent vector. Before we had geometric multiplicity 2 because there were 2 linearly independent vectors. So now we got to put all this stuff together. So let's see how that works. So come on. So we're going to form our D first. So D is a diagonal matrix, and there's more than one way that you could represent the D. It doesn't matter. So what matters is we got to list the eigenvalues across along the diagonal. So we could go, we could list 115, 151, or 511. 511. Which do you want? Pick your poison. 151, 115, 511. So Gerald asked, and was the first one to ask. He said 115. And you might say, how do I know to list 1 twice? The reason I'm listing 1 twice is because of that multiplicity bit that we were already talking about. So that's how I know to have 1 listed twice. So there's my D, and my P is going to be, maybe you can think about it this way. So this one is corresponding to one of the vectors up above. So I would have minus 2, 1, 0. And then this one is corresponding to a second one of those eigenvectors. And from dibs, yeah. Yeah, the 2s and the 1s are the eigenvalues. That's exactly right. 1, 0, 1. Okay. and the 5, maybe another color. I guess I could use orange here. Something like that. And so Gerald asked, what would happen if we swapped the blue and the green columns? If you swap the blue and the green columns, there would be no change. But what does matter is we need to make sure that the orange column that corresponds to 5 is in the same column as the 5 in the D matrix. Okay. You might say, what did we just do here? What we're saying is, if D equals that and P is there, then A is equal to P, D, P inverse. And you should be able to dump those into your calculator and check if you wanted to. You may have forgotten why we care at all. The reason we care about this is this now allows us to tackle power questions. So remember, if we wanted to find a to the 50th, a to the 50th would be the same as P, D to the 50th, P inverse. And it's very easy to calculate D to the 50th. That would just be 1 to the 50th, which is 1, 1 to the 50th, which is 1, and then 5 to the 50th, which is a number that's so big we don't want to write it down. Whereas A to the 50th would be computationally hard to crunch. Questions, comments?
Can you go over the D? How did you get 1, 1 again?
Yeah, good question. So we didn't actually find our eigenvalues ourselves. We were given them, but basically we learned that there was an eigenvalue of 1 with multiplicity 2. And so that gave us 2 of the entries along the diagonal. And there was an eigenvalue of 5 with 1 multiplicity. And so that gave me the last entry. We could have also done, if we wanted, we could have done like 1, 5, 1. That would have been acceptable as well. But if we'd done 1, 5, 1, again, coming from the same places, the 1s here in each case are coming from this multiplicity 2, and the 5 is coming from here, just that there's multiplicity 1. But if we'd used this second matrix, then our P would have changed and the orange column would have been in the middle, because we'd have to have that second column correspond to where the 5 is. Did that answer your question, Adis?
A little bit. I'll stay behind later.
Okay, that sounds good. Hui, you asked a similar question. Did you want to ask?
Yes. Yeah, you already explained it.
Okay. All right, let's do another example, and I think it'll help get at the same thing again. So here's example 4. So in this case, what are our eigenvalues? So I've got eigenvalues of 4 and 5, and specifically I've got eigenvalues of 4, 4, and 5. So we see lambda equal, and we know this because you have a triangular matrix. So lambda equals 4, and you have multiplicity of 2 because it occurs twice. And then we're going to have lambda equals 5, and it's going to have multiplicity 1. Okay. So we don't know if this is going to work. Okay. We're not sure if it's going to work, but if it's going to work, we can already tell what our D matrix is. So if A is diagonalizable, then you can already see that your D is going to equal 4, 4, 5, or some combination thereof. Okay. Okay. Now I want to underscore this if. Okay, so we're not saying that this works, we're just saying if it works. So flip back a page in your notes. What must be true in order for A to be diagonalizable? It's got to be similar to D. Okay, right. And what's our theorem tell us? It says it'll be similar to D, it'll be diagonalizable if what's true. And from Twee and others, that you've got linearly independent eigenvectors. And then Gerlin and James added something important. It's n linearly independent eigenvectors. So in this case, how many eigenvectors do I need in this case in order for how many linearly independent eigenvectors do I need for this to work? From many of you, I need 3. Good. So let me add a word here for a moment. So this is a multiplicity of 1. Specifically, this is talking about the algebraic multiplicity of 1. And for that lambda equals 5, you know there's going to be at least one eigenvector. So there's one eigenvector. Not at least, but there's one. One linearly independent. There's going to be, so there's, we know that because you have a multiplicity of 1. So there's got to be 1. So our only real question is what's going on with lambda equals 4. We can see that it has algebraic multiplicity of 2, but does it have geometric multiplicity of 2? That is, are there 2 linearly independent eigenvectors? So we start same way we did before. We have A minus 4i. That's going to be a very boring matrix. 0, 0, 0, 0, 0, 0, 0, 0, 1. And I've got one mistake, huh? Nice. And right here, this should be a 1. Sorry, it's like something is wrong. Okay. So then we row reduce it. We row reduce, and we get 1, 0, 0, 0, 0, 1, 0, 0, 0. How many columns without a pivot? Abed and Ryan, Felix, James, Dees, there's only one column without a pivot. So you can already see what your answer is. Your one linearly independent eigenvector is going to be 0, 1, 0. So there's one linearly independent eigenvector in that particular eigenspace. And so we would say from all that, we would say that that lambda equals 4 has geometric multiplicity of 1. Because there was one linearly independent eigenvector. Gerald asked, what's the difference between geometric and algebraic multiplicity? That's a good question. Let me come back to that in a moment. Let's see if we can finish this up, and then I'll see if I can clarify what's going on there. So how many linearly independent eigenvectors are there in this particular example? So there's a total of 2. Thank you, Dibs and Felix. And our matrix is 3 by 3. So what can you tell me? If it was, is this thing diagonalizable or not? From Gerline. So I have that the matrix is not diagonalizable. So if it was diagonalizable, then D would equal this thing, but there is no such D. It's not going to work. From Abed, it's not that there's one eigenvector, there's actually 2 eigenvectors. We didn't find the second one. One of them is right here, and the second one we didn't find. It would have been below, but we didn't have to find it because we already knew this was going to fail because there weren't enough in the lambda equals 4 world. Yeah, so Dibs asked, so does that mean we would have to find a to the 50th directly? I think so, which is not cool, or we'd have to find some other clever way of going about things. Okay, let me go back to Gerald's question from a little bit before in terms of the algebraic versus the geometric multiplicity. Let me see if I can backtrack. So if we look at this original matrix here, what is the characteristic polynomial? So characteristic polynomial would be like a minus lambda I, and so you're going to get a 4 minus lambda squared, 5 minus lambda. It was a diagonal matrix, so we can just see that. So the algebraic multiplicity would matches the powers here. So it matches the powers on that characteristic polynomial, or the, like, are they repeated zeros if you like to think about it that way? Whereas the geometric multiplicity matches the number of linearly independent eigenvectors in an eigenspace or total. Does that answer your question, Gerald? Very good. Other questions? So we already said this, but this is a nice gravy theorem. So the times when you know things are going to work. So an n by n matrix with n distinct eigenvalues is diagonalizable. This is just nice. And I think that it actually happens more often than you might think, in the sense that if we just used a random number generator to generate eigenvalue or to generate matrices, presumably the eigenvalues would be generated somewhat randomly as well. And so if they were generated randomly, the odds that you'd have two of them that are the same seem relatively low. So I think this is actually more powerful than you might think. But anyway, so this is a nice thing. It doesn't happen all the time. It's also not a requirement. So if you look at example 3, sometimes you can be diagonalizable even if you don't have distinct eigenvalues. So let A be an n by n matrix whose distinct eigenvalues are lambda 1 to lambda p. Here's our theorem 7. So for k between 1 and p, the dimension of the eigenspace lambda k is less than or equal to the multiplicity of the eigenvalue of lambda k. The dimensions of the eigenspace right here, this is what I'm calling the geometric multiplicity. And the multiplicity of the eigenvalue, I don't remember what color I used. I think I used blue. This is a reference to the algebraic multiplicity. But this particular book just uses the word multiplicity once. They don't have the more nuanced definition. So the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces, that's the geometric multiplicities, equals n. And this happens if and only if the characteristic polynomial factors completely into linear factors and the dimensions of the eigenspace for each lambda k equals the multiplicity of lambda k. Basically, if the sum of the geometric multiplicities is n. And C, if A is diagonalizable and Bk is a basis for the eigenspace corresponding to lambda k for each k, then the total collection of vectors in the sets B1 to Bp forms an eigenvector basis for Rn. So this is a complicated way of saying it's diagonalizable if there's an eigenbasis. Questions about theorem 6 or theorem 7? All right, let's do one more example that I hope will help us to put this together. So example 5. I want to diagonalize this big old 4x4 matrix if it's possible. And so again, when I say diagonalize, what I'm saying is write the matrix A as PDP inverse, where D is a diagonal matrix and P has columns made up of eigenvectors. So I hope you can see that there are 3 different eigen values. So we have 5, we've got 3, and we've got 2 showing up twice. Notice that the algebraic and geometric multiplicities of 5 and 3 are going to be 1. So 5 and 3 are going to be happy. They're distinct eigenvalues. That's going to work. And so our only potential issue shows up around the eigenvalue 2. So what we need to know is, are there 2 linearly independent eigenvectors corresponding to 2? If there are, it's worth exploring 5 and 3. If there aren't, end of the story, go get a milkshake, right? So let's just focus in on that lambda equals 2. And try lambda equals 2 first, as the only way A will not be diagonalizable is if the geometric multiplicity of lambda equals 2 is 1. And so we want it to work. So we have our A minus 2i That's going to be 3 minus 3, 0, 9, 0, 1. And you can row reduce that puppy, and you get 1, 0, 1, 1, 0, 1, 1, negative 2, and then a couple rows of zeros. How many columns do not have a pivot? So 2 columns don't have a pivot. So how many linearly independent eigenvectors are we going to have corresponding to lambda equals 2? There's also going to be 2. Thanks for all that. So is A going to be diagonalizable? Yep, we already can see that A is going to be diagonalizable because we're going to get 2 linearly independent eigenvectors out of lambda equals 2, and then we'll get 1 out of the blue 5 and 1 out of the orange 3, giving us 4 altogether. All right, so what are our 2 linearly independent eigenvectors? So from Abed, I've got -1, -1, 1, 0 for the first. And then from Gerline, I've got -1, +2, 0, 1 for the second. And I know that other people gave me, also gave me those same results. So these are the eigenvectors corresponding to lambda equals 2. So similarly, we could go to our lambda equals 5, and you do all this work, ... and eventually you're going to find one eigenvector, and I got a 1, 0, 0, 0. If anybody wants to work through it, I'm happy to work through the details of where that came from after class. And for lambda equals 3, the orange one, ... I got 3 halves and 1, 0, 0. So notice you have 4 linearly independent eigenvectors. So since you've got 4 linearly independent eigenvectors, we're going to say yes, A is diagonalizable. And so we're going to get that D is equal to something, P is equal to something. So we can write our D's and our P's in multiple ways. Let's mess things up a little bit just so you see what's going on. So maybe I'll write it in the order 1, 3, 5, 1. Okay, so I've got the yellow one first, the other yellow one last. I've got the orange one second, and the blue one third. And it should be 2. Thank you. I don't know what I'm doing. I'm losing it. Like I said, 2, 3, 5, 2. Now am I okay? Thanks for the correction. Okay, so doesn't really matter the order we do this in. So maybe I'll be, again, I'm kind of trying to be almost silly in the order that I do this in. So I'm going to put the -1, 2, 0, 1, which is my second yellow I'm going to put that one first just to show you that I can. And I'll put my other one last. If I can. -1, -1. You could have swapped the order on that and it would be fine. And then our blue one is going to come in here. And our orange one something like that. Okay, so I could swap columns 1 and 4 and it should work either way in this particular case. Felix asked, would it be okay to write the orange vector 3, 2, 0, 0? Actually, I like that better. So if you wanted, you could write 3, 2, 0, 0. Remember, any scalar multiple of an eigenvector would also be an eigenvector in the same space. So sure, whatever makes you feel good. So A is diagonalizable. One last comment, if I may, on diagonalizable. We've learned why we like this because of powers of matrices. So I'd like to briefly tie this back to the Markov chain stability stuff that we were talking about in the videos. And so in the Markov chain world, you ended up with lambda equals 1, and then you ended up with other lambdas being less than 1. They were between 0 and 1. So you had some d that was equal to like 1, and then you had 0 point something, 0 point something, dot, 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 0 point something. And so if you take this D matrix and you raise it to a big power, what's going to happen to all of these other entries along the diagonal? If I take my D to a big power. So all of those green things are all going to approach 0, right? Whereas the red one is going to stay at 1. And so that's part of why we like that Markov chain stuff, why that stability stuff worked, and why it's tied to diagonalization, is that all these other eigenvalues, these small numbers, basically go away. They're not important when we get to big powers, when we take things, when we look at the limit. So it's kind of the, again, a little bit of the connection between the diagonalization, the Markov chain, and kind of all the other things that we've been talking about. So, so you now completely understand everything there is to know about eigenvectors, eigenvalues, diagonalization, applications of that. I can't imagine that you have any questions whatsoever about this. No, that's not true. I'm sure you probably are filled with some curiosity about these things, but we've really ended our introduction of eigenvectors and eigenvalues and diagonalization. And tomorrow when we pick this up, we will start our last application, which is around different types of bases, specifically orthogonal bases and the power that's there. I hope that over the course of the next 2 weeks, you'll learn that, as well as we will all answer the all-important question of how to get rid of the moles. So thanks everyone for another wonderful day. Feel free to hang around if you have questions, and I look forward to seeing you all tomorrow. Take care.